There we go. Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on Twitch. No engines, no libraries. This is designed to show the complete process of making a game from start to finish with every single component and piece talked about and shown how we develop it in detail. And the reason for that is we don't presuppose what kind of a programmer you are or what kind of thing you're building or what you're interested in. We show everything. So if you want to be an engine developer, we do that. If you want to be a game developer, we do that. If you want to concern yourself primarily with animation, we do that. We try to cover absolutely everything. It's sort of like the generalist's course to game development. And right now we're on a particularly important part of the programming, which is optimization. It's the first time we sort of delved into how we make code run faster when it doesn't run fast enough. And we did a bunch of work last week and actually made quite a bit of an improvement to the speed of things. It's roughly about 3 times faster, I think, now than it was when we started, even though we haven't really finished doing the optimizations that we had set out to do. We only sort of introduced some of the concepts and showed how to do the first basic part of it. And so the more advanced part of it is coming a little later, but right now we have some parts that we're trying to do SIMD optimization to our routine, and we have some parts of the routine that we had not SIMDized yet because, as I said last week, they are much more complicated to do in SIMD compared to the things that we were doing. And so what I wanted to start on today is showing you how to do those more complicated things so that you can start to write the entire routines in SIMD, not just the interior math logic. So that's what we're going to do today. If you'd like to follow along at home, you can, of course, always pre-order the game on handmadehero.org. So if you've done that, please make sure you download the source code and unpack day 117 source zip, because that is what I am starting with today, so you'll be right in the right place if you start with that. It looks like I've already got one of these up. I guess I did. Let's CLS that. All right. So let's load up the code and let's take a look at exactly what I am talking about here. We have our new routine, draw rectangle hopefully quickly, and you can see in here that we have done a bunch of SIMD optimizations on this essentially, and saying that they're optimizations is kind of a hard thing to say because it's a little ambiguous. Yes, it did make our code run a lot faster, but actually we didn't really think much about optimizing the code. Really all we're doing is we're taking our code from operating on 1 pixel at a time and making it optimize on 4 pixels at a time. So it's almost just a translation, if you will, which is kind of, it's hard to think of it as an optimization. Now it happens to make things run a lot faster because operating on 4 things at once is faster than operating on 1 thing at once, but it's not quite the same as some other concepts of optimization you may think of where you save some operations by like not doing something that you didn't have to do, which is an efficiency gain, or changing the way that you're doing the math to try to optimize how the processor is doing it, stuff like that. We haven't really done anything like that, but we're already getting significantly faster just by doing this translation. So in some sense, it is optimization, just translating it from scalar C code to the SIMD intrinsics that we're using. So what I'd like to do today is focus on one part that we have not SIMDized. Now you remember this routine here, basically all of the work is done in this interior loop here. And what we've done is we've SIMD'd almost everything except for the part where we load in texels and then the part where we write out pixels, right? And so what I'd like to do today is take a look at just this part here where we write out the pixels, because as you can see, we then downshift very dramatically from doing everything 4 wide into doing things in an ugly loop. And that's not the way we want to do it, because we actually have the option in SIMD of doing this in a much smarter way. So let's go ahead and do that. All right. So the first thing that I'm going to do to make it a little easier on us to start with is I'm going to eliminate part of the problem so that I can just talk about one aspect of it and show you how we're going to solve that. And then later we'll show you, I'll explain how to solve the rest of it, right? So here we are. I'm going to go ahead and comment out this should fill. And what this is going to do is it's going to always draw to the buffer, even if it is outside the bounds of the of the region that should actually have been filled. And what you can see happening here is that depending on that alignment, depending on how many of the 4 pixels spill over the edge of the operation that's supposed to happen, we get a nice old black bar there as we write out stuff that we actually should not have been touching, okay? Now that's totally fine. Like I said, we will put that back in and fix that a little bit later, but what I want to do is take out that aspect of it just for a second so that you can concentrate on the different, on sort of the other part of it, which is just this right? So what we want to do is we want to concentrate on just this one part here where we write things out, and we want to figure out how to do that in non-scalar. Because what we're doing right now is we're looping over this 4 times, and for each time we're building out our pixel manually. And we don't want to do that anymore. All right. So let's flip over to the blackboard for a second, and I'm going to talk about what the strategy is for when you hit something like this in SIMD code, because this is typically the part of the SIMD code that is nastiest. Okay? The part that we did before was always, I said it when we did this, is much easier because, as you can see, it looks almost exactly the same as the code did beforehand. The only difference is we have changed the mathematical operators in C into these intrinsics. So if there was a multiply, we changed it to a function called mulps that just passes the 2 parameters, and that is sufficient to tell the compiler what to do, and we just get our 4 wide operations happening for free. We literally didn't have to think about any of this, and you saw when I did it, it was pretty much a rote translation. Well, this part, especially if you've never done it before, but even if you have, if you're not particularly facile with it, this part is not a rote translation. It's much more difficult than that because you have to start thinking about the SIMD lanes and where they go. So if you think about what happens, we have something coming down the pipeline, right, which looks like this, okay? It is a sort of a set in a SIMD register, or a SIMD value, we should say. We have a SIMD value. It's 128 bits long, all right? So this is 128 bits. Each of these is 32 bits, right? So it's 32 times 4, 128 bits long, right? And each of these is a 32-bit floating point value. So we have 4 32-bit floating point values, and it's like red 0, red 1, red 2, red 3 in our SIMD, right? And then we're going to have one of these for each of the channels that we might need to write out. Right? So we also have, you know, a 4 wide one of G's, right? We've got a 4 wide one of B's and a 4 wide one of A's, okay? And you can see those in the code. They're right here. We actually have them exactly. Blended R, blended G, blended B, blended A, right? So you already see us having these, but remember, each one of these is 4 pixels worth. Now, our problem is that the destination does not look like this at all, right? What the destination in memory order looks like, right, is R0, G0, B0, A0, R1, G1, B1, A1, right, and so on. These are 8 bits, right? So each of these is 8 bits long, 8, 8, 8, right, 8, 8, 8, and so on. Now what you'll notice is we have the same number of actual bits total in flight, so that's fine. We have 128 bits of R, 128 of G, 128 of B, and 128 of A, right? So overall, we have 4 times 128 bits, yeah? So that's all fine, right? When we convert these, we know that each one of them is going to be smacked down from 32 bits, right, down to 8 bits. So this is going to become an 8-bit value, right? So our 4 by 128 effectively becomes a, and I guess this is a little bit misleading. I should probably write it differently. It's not really 4 by 128. It's sort of 4 by 4 by 32, right? So our 32 is going to go, 32-bit float is going to become 8. And what we have down here is exactly the same thing, right? We have 4 of these wide, right? 4 pixels. This is pixel 0, pixel 1, pixel 2, and pixel 3, right? So you have 4 of these wide. Each one of them has 4 components. Each one of them has 8 bits. So once we do our conversion from 32-bit floating point to 8-bit, we will have the exact same number of bits total. So we're not talking about doing anything where we have to increase, amplify or sort of change the total amount of data we have. We have the right amount of data. The problem is that it's simply in the wrong format and the wrong interleaving, okay? So what we want to do, if we were to look at how this would actually be loaded, right? So remember, this is memory order. This is in memory. So this is the 0th byte. This would be like byte 0. This would be byte 1, byte 2, byte 3, byte 4, byte 5, byte 6, byte 7, right? And so here's our RGBA, RGBA. of all the different components, right? And so how many bits wide is this actual guy, right? Well, this guy is going to be, like I said, 4 times 4 times 8, right? And 4 times 4 times 8 is 16 times 8, right? Which, unfortunately, as we can see up here, when we had our 4 times 128, right? The actual amount that we're writing out is going to be smaller than the amount that's coming in. But again, it doesn't really necessarily matter. As long as we can do that conversion from 32-bit float down to 8-bit, it's all fine. So that's not really that big of a deal. All right. So how big is 4 times 4 times 8, right? How big is 16 times 8, right? Well, 16 times 8 is 128, right? It's one of these registers. It's the size of one register. And you can imagine why that is, because in each one of these 32-bit floating point values here, we could have imagined fitting 4 8-bit values, right? Because 32 is 4 times 8, so we can imagine segmenting this register up into 4 pieces and storing them that way, right? So if we look in memory, and this is our frame buffer, RGBA, 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 RGBA for 4 pixels. If we imagine what happens when we load that into an Intel register, right? If we were to load this aspect of the frame buffer, if we were to load this piece of the frame buffer into one of the registers, well, we would, it's Intel little endian ordering, right? So it would take the first 8 and it would put it here. It would take the next 8 and it would put it here, right? And so on. And we would get a register that looks like this, right? This is what we would see. Does that make sense? Hopefully that makes sense to everyone. So this is what it looks like in memory, 0th byte, blah, blah, blah. But again, Intel loads, this is what little endian means. We talked about this long ago, right? Little endian means when you start reading from memory, it goes into the least significant portion of the register, right? So it loads it in here and then continues forwards. What this means is that if we wanted to prepare a register for writing out, right, to the to the frame buffer, if we wanted to write out one SIMD register, we would want it to look like this: R0, G0, B0, A0, R1, G1, B1, A1, R2, G2, right? That's what we'd want it to look like. Because if we had it like that, we'd just store that register directly to the memory and that would do it, right? We wouldn't need this loop anymore. We would just have one giant store, right? We could just say, whatever the pixel is, we could sort of say, pretend that's a M128, right? We could just say that equals, whatever the thing is that we've got, whatever that value is that we've produced, whatever this thing is, we could just write it out. And we wouldn't have to do this loop anymore. We just write out the whole register. All right. So if that's the case, really what we're talking about here, right, our problem is we have to figure out a way to essentially turn 4 registers, each with like R's, G's, B's, and A's in them. We need to figure out how to turn those into this style of register, interleaved. So we need to take something that's effectively RRRR, right? G, 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 B, 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 oops, and A. We need to figure out how to turn that into something that's interleaved, right? So we need to grab like one thing from each of the registers, okay? And so in order to do that, what I want to focus on first, let's just focus on this first, actually. This is going to be probably the easiest way to do it, and then we'll take a look at doing it a little bit differently later. So let's just talk about that isolated problem. Let's just first talk about how would we do it so we could take 4 SIMD values that were looking like this and turn them into 4 SIMD values that look the other way, right? That look interleaved, right? So we want to do it this way, okay? Now remember, this again is the memory order, so really this is the kind of the annoying part of being on little endian architectures. Really, it doesn't look that way in the registers. We're really looking at making it look like this, right? And so on, right? And I guess now that I think about it, I should probably caveat this. I'm slightly wrong in what I'm saying. These are Windows frame buffers, not like OpenGL textures. So actually, they're not even this way. I should caveat what I'm saying here. In memory order on Windows, we actually are BGRA, right? Because remember, Windows has the weird thing where they swapped the R and the G values, right? For how the frame buffer was stored. So really, this is if it was a standard like OpenGL texture or something like this. That's the order for that, which is kind of where my head was. But that's not what we actually want. So really, we need to take these, and we need to produce Intel ordered stuff that looks like BGR, right? So this is inside the register. It should look like this: BGRA, right? BGRA, BGRA, right? So we want 4 registers that look like that. So that's what we want, okay? So let's focus on that first. So we have our blended RGB and A here, and what I want to do is make essentially RGBA0, an RGBA1, an RGBA2, and an RGBA3, right? That's what I want to do. So that's the hard part, but once we get to that, you will notice that there is actually not a lot, there actually isn't much more that we would have to do to finish things off. So maybe what we'll do, well let's do that part first. Let's just do it, and we have to do, there's a couple things that we have to do essentially in order to actually finish things off. So we'll just do it. All right. So let's open up the Intel intrinsic side again, as we have relied on many times, which is handy. And what I want to call your attention to, again, we're only using SSE2 and SSE right now. What I want to call your attention to is this oddly named set of functions called unpack. Now, they're called unpack because they interleave things. And so if you were to unpack something with, say, a zero register, it would expand it in the number of bytes that it takes up. I'll show you what that means in a second here. But if we take a look at, say, unpack high EPI 32, then what this does is it unpacks, and there's 2 flavors of each of these. You'll notice there's an unpack high, and for every unpack high, I'm kind of getting in the way there. My head's getting in the way. For every unpack high, there's also a corresponding unpack low. Okay. Now, what unpack high and unpack low do is they take registers such as these guys, right? And if you call unpack high or unpack low, and then what it does is it targets. So let's say I have my R's and my G's here, right? And I've got 0, 1, 2, 3, 0, 1, 2, 3. So let's say I have my R's and my G's here. If I was to do an unpack, there's 2 kinds, unpack low and unpack high. If I was to do an unpack low, what that would do is it would pick first one from the R, and it would put that into the first slot, right? Because remember, we've got 4 slots for 32-bit values, right? It would take the 32-bit and put that in the first slot. It would then take the G and put that in the second slot. Then it would take the R and put that in the next slot, and then it would take the G and put that in the next slot, right? So you can see that this does that interleaving operation that we want it to do, right? It kind of does that expansion. It's getting closer to this format that we want over here. And so the reason there's a low and a high is because it depends, there's only enough room for 4 values when we do the unpack here. So it's going to use either this 4 or this 4. The high would have done the corresponding thing starting with this guy. It would have produced R2, G2, R3, G3, right? So the unpacks basically target a certain width, in this case 32 bits, and a certain high or low portion to do that kind of interleave, right? So what we want to do is we want to use these unpack operations to take all this data and interleave it. So we want to see it look like this, right? And there's a problem, which is that since the interleave can only be between 2 things, right? I'm only going to be able to interleave 2 things with an unpack operation. What that means is we're going to need more than one unpack operation, and the question is, how do we structure those unpack operations so that we can actually do the unpack to get this actual result? Now what you can see is if I actually target 2 values that need to be next to each other, right? So let's say I wanted to concentrate on producing this GB, right? Well, the GB, if I want to just use the unpack 32-bit, right, and I want to target that GB, Well, that's pretty easy, right, to produce that GB, okay? Because if I've got a vector of G's and I've got a vector of B's, like so, right? So those are my two SIMD registers. If I do the interleave between these two, then what I can do is I can just pick the first parameter to be the B and the second parameter to be the G. And what that would produce is that would produce a B0, G0, right? B1, G1. And then I could do the same thing with the high to get the other ones, right? B2, G2, B3, G3. And now I've successfully produced that bottom value, right? Similarly, I could target the A and R, right? If I have the A's, oops, and the R's, like so. If I have the A and R's, I can do the unpack there the exact same way, so that I can end up with a vector that's like R0, A0, R1, A1, R2, A2, R3, A3. But what you'll notice is, when I go to now combine those results, I want to produce something that's BGRA. What I find is the cascading unpack, the next unpack. There is no way I can still use a 32-bit unpack to actually produce the vector that I want, right? Which is A RGB, right? Because whatever I do, if I was to, whoever I pick, I'm going to have a B, right, followed by an R, which is not what I want, right? Because it's going to pick one from this, one from this, one from this, one from this. What I want it to do is pick two from this and then two from this, and that would give it to me, right? If I had one that picked two from this and two from this. Now, there are unpack instructions that unpack wider, right? I don't know if they actually included that in SSE2. They did, right? So one way we could do it is we could use an unpack, a 64-bit, right, and do the unpack that way, and then that would do it. But what I wanted to show you is actually, and this comes into play sometimes on when you have architectures that don't have multiple widths of the unpacking, or you want to do other stuff. We'll kind of see things a little bit later. Is that if we don't do it that way, if we instead mix the other two values in the first step, we can actually just use the same width to do all of our interleaving, right? So let's say that instead of doing it this way, right, we actually do it slightly differently. Let's say that instead we mix the R's and the B's together and the A's and the G's together, right? So we pick B and R, right? So we end up with B0, R0, B1, R1, right? We pick that first. And then we pick the A's and the G's. So we have G0, A0, G1, A1, okay? Now, if I wanted to do the mixing on these two, if I pick this is the first parameter and this is the second parameter, I get B0, G0, right? R0, A0, right? That makes sense? Here, 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 here. And so what you can see is as long as you pick your mixing order correctly, using a single width, you can actually go ahead and do the complete shuffle that you actually wanted to do, all with one type of instruction. Now, is there any real reason for us to do that here necessarily? Not necessarily, but it's an important thing to understand how these shuffles kind of work like that. It's just an important thing to sort of think about because, you know, when you start working with these things and you've never worked with them before, stuff like that may not be clear to you, right? It may not be clear that you can always get the shuffle you want by picking the order properly. So I'm going to show how to do it that way just first, and I guess I already sort of did. So you can see what we essentially said. We needed to do one unpack with B's and R's, one unpack with G's and A's, and then we need to unpack the result. So let's just go ahead and do that. Not very difficult, but essentially what we have here, right, is we've got that BR, sorry, I guess I should say, I'll name them in register order. So really what these are going to be, just so we can keep our naming scheme, oops, ARGB, so we can keep our naming scheme kind of clear here so that anyone who reads the code knows what's going on. We'll keep them all in register order consistently throughout. So what we need to do here is produce the B0, R0, B1, R1 vector, right? And so we're just going to say that exact thing. This is R1, B1, R0, B0, right? And then the next one is the AG, A, G, like so, right? Hopefully that makes some sense. And then all I need to do here is do that, that unpack. And again, these are both going to be low unpacks because they're unpacking the 0 and 1s, not the 2s and 3s. So these are both going to be unpack lows, and they're going to unpack exactly what they said they were. Now, we have to double check because, again, like I say, parameter order is always a little weird in these things, so I always have to check to make sure I know which one it's considering the low. So the A in this case, right? Sorry, this is unpack high. They're the same parameter order, but let's at least read the correct one. So unpack low, EPI 32, right? I'm just gotta type that in. Gotta at least type it in correctly. So unpack low, EPI 32 here. What we need to do now is just take a look at who actually is the person who goes in the low slot. And let's see. So that is dwords 0 to 31 comes from source 1. Now, of course, it's awesome that they use A and then say source 1. All right. Well, we'll assume that A is source 1 for now. So source 1 is low. And since we want in low to be B, we'll do it this way. But we can step through the code and verify that that's true, I suppose. That seems like a reasonable thing to do. And so we want B and R. So there's B, there's R, and then here we want G and A. So there they go. And for now, I'm just going to if0 these out, and leave the code running otherwise as is. Oh, and this is, of course, an MM128. Sorry. All right, so one other thing we have to address here, which I did not address, is the fact that, again, and this actually brings up a point that Fabian mentioned the other day to me. So MM128i is, of course, like I was saying when we first introduced this, it's whether or not it's treating it as integer or floating point. And Fabian actually pointed out something that I did not know, because I don't really, I've never had to really do any hardcore SSE2 optimization, to be honest with you. Like I said, the only time I've ever really done super hardcore stuff was on the Xbox 360, which was not in any way SSE. What he said, because I thought the M128i versus M128 was purely a typing thing for C that the intrinsics introduced, but it's not quite. It's actually a hint to the compiler or a guide to the compiler in terms of picking the instructions that you're trying to do, because it turns out that there actually is different unit in the CPU for doing the integer operations versus the ones that do the floating point operations. And sometimes you will lose a cycle here and there if you move between the two types. So it is worth, at the limit, and probably not in anything that we're doing, but if you really care, it is worth paying attention at the limit to how often you have to move between an M128 and an M128i, because it actually may not be free, and Fabian said it changes depending on the architecture as well. So just something to keep in mind. That's what Fabian said, and he is usually right about these sorts of things. So what we need to do here is we just need to change the type of this, and you can see that there's actually casts for this, right? There's basically like a cast that converts one to the other. It's called cast PS SI128, and there's the same one which is cast ISI 128 to PS. So basically, it's free for us, sort of at least nomenclature-wise, to switch between these at any time. So if we want to use integer instructions, we can do so, right? All right. So let's do the cast here. We want this one, right? Oh, sorry, we want, where is it? This one, right? So we want to turn a floating point value into the integer value, like I said. So let's go ahead and do that. Let's do, what is it? Cast PS SI128. There we go. And we'll do it here. And again. There we go. All right. So there we go. And what you can see here, when I compile this, what I'm going to do, I want to show you how this works. What I'm going to do is, again, we've talked about structured art many times before. What I'm going to do is use essentially structured art here to make it easy for us to see. This is almost like when you do like a medical procedure and you inject like radioactive dye into the person to see where things are going. We're going to do exactly that. So what I'm going to do is I'm going to overwrite basically the stuff that's in these registers. So I'm going to use set PS, right? Like so. And what I want to do is I want to basically set it up so that it's really trivial for us to see what's going on in the registers as we do our shuffles. So I'm going to do a set PS. In fact, I think I might actually do it as a cast here as well. So I'll do it this way, where we actually, I think I want to actually do it as a set EPI. Sorry, my brain is blanking. A set EPI. I want to actually set basically a what amounts to hexadecimal values, because they'll be easy to see in the debugger. In fact, I guess I could even do this in a way that's even a little jankier than that. What I could do is something like this, you know, the R's, and they're going to basically be something that looks, I think a 5 kind of looks like an R, maybe. So I'm going to set this up to be like R0, R1, R2, R3, right? You can kind of see the R values like that. Does that, I don't know, does that make any sense to anyone? I feel like that's sort of makes at least some sense. So I'm just going to do it that way to basically just make it really clear where the values are. And so I'm going to do that and then say 28 RS, like so. So I'm basically just going to load in those hexadecimal values into the RS. And I want to do that with absolutely everybody. So I want to make, you know, basically, you know, a GS, a BS, and an AS. And the nice thing about that is the A's actually can be A's, and the B's can be B's, right? Let's keep going through here, right? Right. And I guess since this is actually memory order here, now that I think about it, I've actually got these guys not quite right. Rectangle. Again. Switching between memory order and register order is always kind of a little bit of mental gymnastics. Anyway. Kill rectangle. Rectangle. There we go. So yeah, and also the G's, again, can't quite do. It's unfortunate hexadecimal stops at F. I'm not sure what is a good thing that kind of looks like a G. Maybe C, let's say. It's almost a G. It just, you know, it needs that little extra curl at the end, and then it would be one. Maybe, I don't know. I think it's the best we're going to get, so we just have to accept it for now. Anyway, and let's move that last rectangle. Okay. So, again, just finishing up here, making all of these A's, making all of these B's, making all of these C's, and those guys up top are already 5s. Last time, C, B, A, B, C, C, B, A, B, C. It's almost the alphabet song. And then each of these guys, again, I'm just going to override what's actually supposed to be in there so that I can use that as sort of our little radioactive tracer, so we can see what's going on and just, you know, be sure of how the sort of shuffling works. All right, so I guess this doesn't need, this is an array, so it doesn't address. There we go. So let's go ahead and set a breakpoint there. I want to switch us back to debug mode for the moment so that we don't have the compiler doing anything at all. We want it to be completely stock, right? So I'm going to get rid of that O2. We should probably put the O2 at the beginning so it's easy for us to change. So that's the only parameter we ever modify. Anyway, So coming in here, I'm going to stop here. And when we load those guys in, essentially what I want you to be able to see is when I go into the watch here, and I've got blended R, blended R, blended G, blended B, blended A, is that if I want to, I don't actually love the way these guys get displayed, to be honest with you, because it's hard to actually see exactly what the register value actually does. I don't know if there's a way to, nowadays in Visual Studio, give it kind of an extended register thing. But we can look at it in kind of a couple different ways. One way would be to just look at the M128U32 value of it, which you can see has the values in there so that they're pretty easy for us to see exactly where they are. And again, this is just a little bit easier than trying to use, at least in my book, is than trying to actually use like 1, 2, 3, or 4. But that would be the other way to do it, is if we tried to use like, you know, some kind of number coded thing. So anyway, what I'm going to do is I'm going to tell the compiler to just, tell the debugger to just look at that value so we can see 128U32. And so just on one line, we can see what's in that register, right? There it is. And I guess I shouldn't say register, just that value. We don't know if it's in a register at the moment or not. There we go. Oops. Right? So there's our values, and you can see we've got our quote-unquote R, our quote-unquote G, and our B and our A, and we've got the different ones for different pixels. So this is the 0th pixel, this is the first, the second, and the third, right? Now what we're going to do is we're going to come in here and build our hybrid values. So here is R1, B1, R0, B0, right? And what we want to see is we want to see that value actually produced, right? So let's do that here. What is this saying? Let's see. Sorry about that. It's a 128i, right? Of course, because since they had to rename the member. All right. So now that we've produced this, we can actually see whether this is what we've got. And unfortunately, it's listing these now in memory order, of course. Again, things. It's always a struggle with the little endian, because you always have to remember which order they're actually doing things in. But when they list things in C arrays, they always list them in memory order. So we can't actually see the register by itself. If we were to look at the register, of course, here is the register, and you can see it in register order, which of course is going the other direction. It's all fantastic, right? That's just the way it goes. But anyway, you can see here that we got what we wanted. B0s in the bottom, R0s in the next, B1s following that, and R1s following that. And so again, all I did here was I used the structured art technique to make sure that we knew what we were actually doing, right? And especially when you're first working with these, to get comfortable with them, it helps to have very clear values. Because if these were just random floating point things, we'd be like, I don't know, okay, wait, what was the R again? It was 0.0395, or everything was 0, so we couldn't tell what moved where, or you never know, right? And so in this case, it's much easier. Here we can see we did get our G0s, A0s, G1s, A1s, right? So we've got it. And so basically all I've done there is just verified that we got the exact unpack that we actually wanted, right? And similarly, I can go ahead and do this for any arbitrary number of these, but what I'm going to do is I'm just going to produce one final value here. I'm going to do the unpack low on these guys, excuse me, to unpack that 0th pixel, right? Like so. So here's R1, B1, R0, B0, and here's A1, G1, A0, G0, like so. And similarly, we could actually produce number 1 here as well, just by doing an unpack high, right? So here we go, and off we go. So let's take a look at what we actually produced at ARGB0, right? And you can see if I take a look at the value that we produced there after this next shuffle, we got exactly what we want. We got B, G, R, A, which is the memory order that we wanted. RGB1, M128i, U32. Same thing, but now it's the first pixel. So what we've essentially done here is produced 2 correct packed pixel values. Unfortunately, We still haven't quite gotten to where we need to go, not just because we haven't produced the rest of the values yet, but also because they're still in 32-bit floating point, right? But let's finish just so we can see exactly what's going on here. What we would need to do essentially is unpack the high bits of these guys, right? And by unpacking the high bits, what we do is we change from extracting those low pixels to extracting the 2 high pixels. And then we would do exactly the same unpack here for 2 and 3, right? That's it. It's literally the exact same thing. There you go. And although it's kind of meticulous and fussy, really there's not much to it. You know, that's really all there is. And if you come through here, you can see now we have actually produced all the pixel values that we actually wanted. The problem is that they are just in the wrong format. They're still 32-bit float. But there they all are, right? There's the interleaved pixels, and off you go. Now you can see that already it's kind of annoying. Like, look at how many instructions it took us to do that. It's kind of grumpy, right? But that's just the way it goes with SIMD sometimes. When you have to take things that were in the nice SIMD format you're working on and shuffle them around to put them off into an interleaved source, that is always kind of annoying. And so you can kind of see it happening here. But we can, you know, we might be able to do some mitigation of that, as you'll see as we go a little bit forwards. I'm going to leave the structured art stuff in here so you can see. But now let's talk about the second part of this problem. So you saw how we did interleaving. Hopefully that's pretty clear. Again, it's very fussy, but it's pretty straightforward. All we were doing is using one one pair of instructions, low and high unpack of 32-bit values to do basically that twizzling. And what we had to do is essentially to produce 4 pixels, we had to use 8 unpacks, right? That was that. All right, so now we have to talk about another thing, which is how do we generate values that are actually going to be what we needed them to be, which is 8 bits instead of 32-bit floating point. And so in order to do that, well, we've got some things that we can just do, right, certainly. We can certainly do a plus 0.5. That's something that we know how to do, right? We can certainly do a times 255. That's something that we know how to do, right? So we know all these sorts of things. So you can see we already are doing the times 255 up here, so we've already converted it to that range. So all we really need to do to finish off what was happening down here is to take that plus 0.5 and translate that up here. So that's something we can just do, right? That's something that we could have just added to this, right? We could do an add ps. So if we need to do that, we can. But let's quickly take a look first to see at what's going to happen when we need to actually produce integers instead of floats. So what we have for that is there's conversion instructions. You can see them here. They're called convert. And so like you can take a look here, convert PS EPI32, convert packed single 32-bit floating point elements to packed 32-bit integers and store the result in dest, right? And so that's exactly what we want to have happen. This is the thing that we wanted. We want to have a way to convert our integers, our floating point values to integers. And you can see that it's just a single instruction that does that. It's not particularly difficult. It's convert PS EPI32. So what we can do here is we can actually just do that, right? We can make a MM128i. That's basically our int r or whatever we could call it, right? And that's just going to be calling that intrinsic. Convert PS EPI32. And again, that naming convention is basically PS is packed single, EPI32 is extended packed integer 32-bit, right? I believe is what that is. I believe the E is for extended. To be honest with you, I don't think I've ever actually been told what it is. I just assumed. And so, yeah, packed integers that are 32 bits wide. So that's what we're going to do here. And again, all we have to do is just do that to convert 4 of them at once. So we have this converting each of our values, and it takes 4 of those instructions to convert each of our things into integer. And there they are, right? Now the question is, when it does that conversion, what rounding mode is it using? Is it using truncation? Is it using round to nearest? What's it doing? Because if it's using round to nearest, then we don't need to add the 0.5. If it's using truncation, then we do, right? And so we kind of need to know what the rounding is actually going to be. Now, unfortunately, there actually is no way to know what the rounding mode is going to be unless we set it, because the way that the SSE registers actually work for these operations is they actually use a mode that says which way things should be rounded. And that mode can be set to any number of different rounding methodologies. So what I'm going to do here is I'm going to do set the rounding mode to something known, and we'll come back to that later. For now, we'll just assume that it rounded in the way that we wanted it to round, and we'll deal with it a little bit later, right? Because that's a separate concern. All right. So once we have these into integer format, we now have another problem, which is that they're 32 bits wide, but we actually want them to only want to use 8 bits out of that, right? So what we want to do is we would like to be able to, get these things together in some kind of a more useful fashion, right? Okay. So we covered how to do it this way. We covered how to do the interleaving if we were trying to interleave the things as floats. But let's take a look at what happens if we now have integers, right? So we have integers, and we know that those integers are going to be 8 bits because we clamped them already, right? I believe we already have a clamp in here. You can see our min, max, PS. So we know they're between 0 and 1, and then we multiply them by 255. So we pretty much know what the integers are that are coming out of here, right? And the integers, are going to be 32 bits wide, okay? But only the bottom 8 bits are going to be used. So we're going to have 8, 8, 8, 8, like so, right? So we're going to have, the R's looking like this, R1, R2, R3. And then we're going to have the same thing happening, right? With the G's, G0, G1, G2, G3, right? So if you look at these, we may, right, if you look at how these are lined up, we could, because we know all of these is 0, right? All of this is 0 in here. What we could do, instead of doing the kind of interleave that we had to do if we were trying to produce them actually as floating point, right? What we could do instead is we could just shift up. If we could move, these 8 bits to the next 8 bits over, to here. We could then just OR these registers together to produce the correct values, right? In other words, we could do the same ANDing and shifting operation that we were doing here, where we shift them up. We could do the exact same thing for the wide registers, right? So let's see if we can't do it that way. I showed you how to do it one way here. And what we could have done here is, convert these to integers and then pack them down or something. But let's try doing it the other way. All right, so I'm going to go ahead and if zero out this, like so. Okay, so I'm going to get rid of all of this. There we go. So if we've got these, let's see how we would do that. Well, we know that we want the lowest value to be B, right? So if we were to do, we already know that we could basically do all of our math ops, and you can see, actually, I guess we haven't ever shown this one, so let me just show it here. or PS. You can see that we have bitwise operations on these guys. So if we want to, we can go ahead and OR in values together, right? So all we would really need is the ability to shift them around, right? We can OR them together, but we don't have any way to shift them around. So I can, if I want to, produce my outgoing pixel value, like my result value or something like that. I don't know what we'll call that, our out value, I'm not sure. We could go ahead and do that by putting together all of these things, right? Like int r, int g, int b, int a, like so on, and just ORing them all together. But what we don't know, right, is how to do the shifting, right? So we've got all these values, but we have absolutely no idea how we would shift any of them. Excuse me. All right. Did I do that right? So this or this, that or this, that or this. I don't need 4 ORs. I only need 3. There we go. So the problem is, how do we actually shift these guys, right? So what we want to do is we want to find some operations that actually do shifting. So I'm going to check the bit manipulation one here so we can take a look at them. Although I don't know why it's not actually showing me anything. I guess why? Oh, here's shift. I guess bit manipulation is something else. So here's my shifts. And what you can see about the shifts is, unfortunately, the shifts are all... oh, wait, never mind. I was about to say unfortunately, but that's not true. We are not actually in floating point anymore. Sorry, don't know where my head is tonight. My bad. So that's fine. So our shifts are all on SIs, which is what we want. And you can see here that we have a number of different options for how we shift. And what they are is they're what the width is of the shift, right? So what you can see there is essentially, like some of these things like shift left and so on, what they will do is they will clip when they do the shift based on the width that you say. So if you do a 32-bit one of these, if you do the EPI 32, where it's talking about 32-bit wide, then bits will shift up until they hit here, and then they will just shift out, right? They won't cross this barrier. Whereas if you were to use the 16-bit wide version, you would actually start clipping out on the 16th bit. So you'd shift up, but when you hit the 16, you would stop, right? So basically what this does is it picks the compartments for the shift. And you'll notice there's two kinds of shift. There's for shift left, it's always logical. But for shift right, there's two kinds, logical and arithmetic. And what that is just to quickly say, since we haven't ever covered that in Handmade Hero, when you're shifting values left, then the bits that shift in from this side are always 0, right? So if I had some value like 111, right, or whatever, and I shift that left, then I know that I'm always going to fill in the spots that I shifted with zeros. But when you shift right, there's two things you could fill with. So let's say I have 1110000 or something like this, and I want to shift it. If I want to shift it that way, I could fill it in with zeros, right? Or I could fill it in with whatever the high bit is. So if the high bit is 1, I could fill it in with that, so I'd get this, instead, right? And the reason they do that is because 2's complement, the way of storing negative numbers, right, always has the high bit set if the number is negative. And so if you want to use a shift to approximate dividing, if you want to use like a divide by 2 to do the shift, you want to keep the number negative if it was negative originally. And so the shift does that arithmetic shift. That's why it's called an arithmetic instead of a logical shift, because it's for when you're doing arithmetic. That's what that is. We don't care about that at all right now. I just wanted to mention it as an aside. Okay. So to get these things lined up, all I need to do is I need to do a 32-bit wide shifts, and I need to shift things up by 8, 16, or 24, the same exact way that I was doing it down here. So we're literally going to do an exact translation of this code, right? So the A gets shifted up by 24, right? So I'm just going to throw that in there. I want a shift left logical. And also I should mention one more thing. So there's two things here, shift left logical immediate and shift left logical. Shift left logical immediate shifts by a fixed value. Shift left logical without the immediate shifts by another register that tells it how to shift. We don't need that right now, but you can see why that might be something interesting, right? Okay, so we're going to do the shift left immediate. We need to shift the A up by 24, so there it is. We need to do the shift left logical, oops, I forgot the EPI 32, EPI 32. We need the the shift left logical immediate of 32 here for the B. Well, I guess we don't. The B stays in the bottom, right? The B doesn't actually go anywhere. So for the G, we need to shift that up by 8. And for the R, we need to shift that up by 16, right? And so now we're back to doing the exact same operations we were before, right? And off we go. Now, I should actually point out that ORs and ANDs don't actually care what the width is because the bits get treated, there's no movement. So really, I believe the mnemonic for OR is always the same. You don't actually need the EPI 32 or to say what the width is. I think it's just SI 128 all the time. That's my recollection anyway. Let me see if I'm right about that. OR, oops, or, Yeah, it's always SI128 because you don't care. It doesn't move bits around or carry or add or any of that stuff. So it's always the same, right? SLI EPI 32. Did I use the name wrong? What did I do there? Give me my shift back. SLLI EPI 32. Oh, I had an extra underscore, that's all. All right. So let's take a look at that out value now, if I may. Let's see here. After we produce it here. Oops, stop it there. So let's take a look at what that out value ended up being. We have our, oh, my bad. I take it back. We don't actually have our structured art in there. So what I want to do is I want to move the structured art up here so I can actually overwrite these after their conversion. So what I want to do is I want to say that, each of our, our int r, our int g, our int b, and our int a, there we go, are all going to be loaded with those sort of faux values, if you will. And I guess these now integers. There we go. Okay. So off we go. And let's see what we've got here. So our out value, well, first let's see what our int r and so on values are. Dot m128 u32. There we go. So each of these should be the correct values here. There we go. G, B, A. Okay. So we've got all the values that are what we think they should be, right? And then we have our out value, dot m128i u32. And let's see what it equals. So that is not what I wanted at all. What is that? What are those F's doing there? It's not at all correct. Our B's are correct, right? But our other values are not correct, and I'm not sure why, right? So let's take a look at what I wonder if I use the wrong thing here. Let's see. Shift back 32 in a left by immediate 8 while shifting in zeros and store results in dest, right? And so, oh, is that? Oh no, I can. No, that's fine. I can shift as many as I wanted to. So what was the problem here, people? Let's take a look at what happened here. I want to see what the actual values are. So I'm going to break out this routine a little bit further, but then we're pretty much done. So hopefully this will be like the last thing we do. So let's do our shifted values here, right? G, B, and A, and then I'm going to go ahead and just grab these guys out of here, right? There's our G, there's our B, and there's our A. SR, SG, SB, SA. And so now I should be able to inspect these, right, and see what the oddity is there. Let's go ahead and run that. And so our SR is as follows. That is, oh, well, I was hoist by my own petard there, as they say. I forgot. We're expecting these values to be in the range of 0 to 255, so we were expecting these to already have been zeroed out. So yes, my test case was not particularly well constructed. I admit that. So let's go ahead and try that one more time. See if we can't get more reasonable results. Yes. So obviously the stuff coming out of this pipeline will always be 8-bit because we clamped it. So we know that we've only got 8 bits in each case. All right. There we go. Much better. So now, if we do this, hoping, yeah, we will see our stuff much more intelligently lined up. And there we go. So there's B, G, R, A, B, G, R, A, B, G, R, A, B, G, R, A. And so as you can see, essentially, I taught you how to do the unpacked version, which is if you needed to interleave the things as float. But as you saw here, in the case where you don't have to interleave them as float, you can actually do it almost exactly the same way that we were doing it here. Because you happen to have the small values all sitting in the registers in the right places, you can just shift them over and sort of do that OR. So if I get rid of this part here, right, if I clip this stuff out, what you can see is that now we've set ourselves up to essentially do this whole write here, right? So I can take that out and I can essentially just write it to pixel, right? I can stay, if I pretend that pixel is an M128i, right? I can essentially just assign out to it, and that should write out the values that I produced packed, right? And so if we take a look at that, we can see that we've essentially gotten exactly what we had started with, which is the black bar version of the blit, right? But that removes that entire thing there. And if we go over to O2, right, we should also see that it didn't slow us down at all, right? Uh-oh. I know what that is. Okay. Thank you, Visual Studio, for crashing in the middle of our debug session. That's not good. I know what that, well, at least I believe I know what that is. But that would be a topic for next time. I don't want to dive into that yet. I assume that's Microsoft wanting us to be aligned, but of course we are not aligned. Let me see if I can make that crash happen. I was kind of hoping I could make it happen in a way that wouldn't crash Visual Studio so I could show you what we were talking about there, but, wishful thinking perhaps. So, let's take a look and see if I'm correct about that. Let's see here. Well, I guess this is the value. So there we go. That value. So what I assume is happening here, and we could take a look at the disassembly, is sort of a next topic that we haven't quite addressed yet, but I just want to mention what it is briefly. Where is the instruction pointer, people? Show me the instruction pointer. There it is. I assume what is happening here is that it's trying to write to something that is unaligned. Well, actually, I can see that it's trying to write to something unaligned. Well, I should verify that fact first before I say that. Let me see. Can you show me this value? RDX minus 10H. There we go. So 21EB4B8. What is that value? And 15. So there we go. Yeah. So I assume what's happening here is that move DQA is unaligned. And unfortunately, on the Intel processors, when you write to an unaligned address, you get a crash, right? And so presumably in debug, it was not using the aligned write. But I'm going to just see if that, I just want to verify that just so we make sure we say it. If pixel and 15, 0, and I'll give a little bit more of an explanation of that in a second. So if, what is the problem here? Pixel is, you don't want me to, all right. Well, if pixel has a uint64 then, how does that strike you? There we go. All right. So here you go. And what you can kind of see here is that basically if we only write when we are aligned, we don't get the crash. But if we allow it to write always, like so on, then we get the crash. So I don't really want to belabor that topic because that was something I wanted to talk about later. I assumed it would do sort of it would do the safe unaligned right there. It didn't. So I'm not sure exactly how to tell it, please don't do an unaligned right now. We're just doing some test code. But basically what happens here, to give you a little perspective on that, is these things are 128 bits wide, right? So 128 bits that's 16 bytes. And the way that the Intel processors work is they have instructions for writing aligned and writing unaligned, right? So what we have is 16-byte boundaries. It's considered aligned if essentially you write only to every 16 bytes exactly, starting from like the 0th base of memory. We talked about this, I think, a long time ago. Starting from the 0th point in memory, alignment basically means that every 16 bytes, right, 16, 32, so on, right, there is an alignment boundary. And it never wants you to write to, say, the 3rd byte. You know, it doesn't ever want you to write like that. It wants it always to be aligned. So what that means is that the pointer, right, the bottom part of the pointer should always be 0, right? Because 16, right, is 2 to the 4th. So the bottom 4 bits of the pointer should always be 0 if you're writing. If you're not, then it will issue an exception. Now, it has ways to write unaligned. Some processors don't. Some processors, when they're doing wide writes like that, you have to write aligned. But the Intel processor actually has the ability to write unaligned, and I believe by using an intrinsic, we can force it to do that. So let me just do that quickly so you can see. So here's the store instructions. And I believe mmStoreU SI128 is the one we're looking for here. So it does not need to be aligned on any particular boundary. So if I want to, I can go ahead and do that. What I can do is actually issue this intrinsic mmStoreU EPI, SI128, right? And then I can go ahead and use that pixel pointer and that out pointer like so, and that out value like so. And this will cause it to issue a separate instruction. So let's go ahead and take a look at that now. If we go, remember it was using move DQA there. If we go to the disassembly, you can see now that it's actually not doing that move DQA. It's using the regular mov instruction, right? And that does not have to be aligned, right? Assuming that that's actually how it did it. Let's just double check. RDX, pixel, yeah. So that's it. And so here, we're fine now, and we're back to the way we were doing it before. But again, that alignment thing is kind of a little bit of an nastiness. And you can see we're continuing to get actually faster just by doing this translation. We were at 120 cycles. We're now down closer to 110, right? So we keep going a little bit further. So that is the end of the stream. We're already a little over time because I wanted to just mention briefly what that was. We'll talk about that alignment later because the alignment is actually important, and it's something that when we're done doing this routine, we want to step back a little bit and look at alignment as something that we actually care about. But we don't want to get into that just yet. That's why I don't really want to talk too much more about it. But basically what we've done now, as you can see, is we've sort of removed all of that looping that was happening at the bottom now. So there's no longer a need for any of that looping. We build directly the 128 bits that we want right in the SIMD registers, and then we blast them straight out. And it didn't cost us that much to do it. It was 8 instructions to prep everything. And I guess not 8 instructions because this is a no-op instruction here, right? So it was 7 instructions to prep everything, and then 3 more, so 10 instructions total to get it down into that packed format. So that's not bad, right? That's not bad. And again, that does 4 pixels at a time, so it's actually pretty cheap. All right, so let's go over to the Q&A now, because I would like to take some questions in case there are questions on that. There we go. Again, I showed 2 ways to do that interleaving. One way to do the interleaving is with the unpacks, and that's if things are staying in floating point and they have to be interleaved. In our case, we don't have to write out the floating point. We can just write out the bits, and so we did it this other way, which is to first convert them first to 32-bit integers, and then to shift the integers into place and OR them just like we were doing, kind of the analog of what we were doing, only 4 at a time. So that's very straightforward compared to it's very similar to the scalar path, right? The 4-wide path looks almost exactly the same. It's just using intrinsics instead of the infix notation. Also, I will put in the 2D for what we're doing tomorrow. Write only the pixels, so that should fill equals true. Right? Will the operations be recorded to reduce the number of ops and load stores? So here's what I would say about that. The compiler often does a pretty good job with that ordering. So we may be able to, like when we're totally done with this routine and we're satisfied with everything, which we gotta first handle the fact that we're not obeying should fill here. That's pretty easy to do, but we didn't get a chance to cover it today. And then we need to do this part up top, which is fairly complicated. So we need to do those things. When we do those things and we're done with the routine, so we have the complete routine, what you're talking about is essentially you're saying, can we reorder the order that we put these things to reduce the number of loads and stores that have to happen, or things like this? And the answer is, if it's algorithmic, perhaps we can. But if it's simply a question of trying to schedule the assembly that way, usually the answer is no. Because the compiler has all the information here, and it typically chooses how it schedules the instructions. So depending on, unless the optimizer is really bad, there's not that much we can do with reordering these things, right? Because not only is the compiler going to reorder them to try and schedule them well, but the processor reorders them, remember. The processor has a window of several instructions that it's going to reorder in. So the order that we put them in is not the order they're actually going to get executed in, right? So there's a limited amount we can do with that scheduling, so keep that in mind. Momoizuko, you are calculating out or RGBA. Would it be better to do it like this, or RG, or BA, so the first two ORs are not dependent on each other? Yes, I suspect that would probably be better, but again, let's take a look here. I want to just to underscore this point. Let's see. Oops. Why you no want a break? Why you no want to set a breakpoint, Visual Studio? There we go. So let's take a look at the disassembly here, right? And see what it was actually doing. So where are the actual ORs? Mul PS. Mul, we're doing all our multiplies and so on. Doing multiplies here. And add PS 6 and 0. Add PS, add PS. So I feel like, if I'm not mistaken, I feel like it has optimized out that expression entirely. It's not doing it that way at all. Am I right about that? Oh no. Okay, I'm like, how did it do that? It's just massively reordered this routine quite a bit. Here's the part we're actually talking about. All right. So here's the P OR, right? This is where it's doing the first OR. Here's the next OR between the same two registers. So it's actually done, it's done a bunch of sort of reordering here, right? I'm not sure. It's decided to load in the Texel A. I mean, it's kind of hard to figure out exactly what it was doing, The shifts are dependent. They happen one right after the other. I don't know how much, again, like that matters depending on how the processor's working, but you see the POR here, then it's doing the reconversion, then it's doing the OR here. So you can kind of see that it already spaced them out quite a bit. So while it's probably better, I would say it is probably better to write it the way that you were suggesting, meaning writing it this way at least makes it clear to the compiler that we didn't really care about them being done serially. But I suspect that the compiler already knew that, if that makes sense, and won't really generate anything substantively different, if that makes sense. But I don't know. So you can see here it's issuing the two ORs together. So it didn't feel the need to spread them out. So, you know, maybe that gives it a little bit more flexibility. Like it decided to do that and it couldn't have done that before. I don't know. I really don't. But you can see it's in fact, I guess now I think about it, that's actually bad though. That's the serial OR. It actually didn't issue the two ORs together. It issued the first OR up here, the second OR here, and then the combining OR it did down here, right? Does that make sense? So it's now issuing them back to back when before it wasn't issuing them back to back. So yeah. So I don't know, like when you're dealing with intrinsics like this, I realize it's tempting to try and think like an assembly language programmer and really try to do assembly language kinds of optimizations. But what you have to remember is that unless you're actually just looking at what the compiler's doing and trying to shuffle things in intrinsics to make the compiler do something different, what you're writing here in assembly is not what's coming out in assembly directly. So you have to take these sorts of things with a grain of salt. This may or may not produce better code when you actually run it, right? Just because it breaks up what appears to be a serial dependency, it doesn't necessarily mean that it's faster one way or the other. So we can time them and see at the end of the day, but you know, it's a crapshoot. That same thing would not necessarily be true if you were writing the assembly yourself, because then you may decide to schedule them one way or another. But the other thing there to remember is the processor, again, also reschedules things. So it's still pretty hard, even at that point. You'd probably still have to time it to see whether it mattered at all. Do you need to start with 32-bit floats? Is there further optimization that doesn't need the casting? So remember that we're not doing any casting. So there's no more casting, right? We got rid of the cast entirely. What we are doing is conversions. That's converting between float and integer separately. And so the answer is, well, you could try to do this pipeline in integer, right? You could choose to try to do it in integer. And if you look at the sort of things that we're doing, it is not out of the question that we could try to do this in integer. And furthermore, although it probably wouldn't be any faster to do it in integer, because we constantly would have to introduce shifts, right? I mean, let me just make this explicit. So basically, if you think about trying to do something where you've got integer times integer equals integer, right? Versus float times float equals float. This path always just works. Float times float equals float, that's one instruction. Integer times integer equals integer in our case is not one instruction. Because what happens is, this is actually a number between 0 and 255, right? And 0 to 255. This is between 0 and 1 and 0 and 1, and we want the output to 0 to 1. A number between 0 and 1 times another number between 0 and 1 equals a number between 0 and 1 in floating point. And the floating point unit does the adjustment to make sure that that remains true. In integer, there is no such thing. So when we do a number 0 to 255 times another number 0 to 255, what we get is a number 0 to 65535, right? That's what we actually get. Make sense? So if we do that, what that means is in order to use this in the pipeline later, we then have to shift it down to avoid blowing out the precision of the register. So we need to actually follow each mul with a shift, right? Does that make sense? So it actually becomes very expensive to do the pipeline in integer. So typically converting to floating point once at the head end and converting to floating back to integer at the back end is actually faster than trying to do everything in fixed point, if that makes sense. Same for texture bilinear adds together. Yeah, so, excuse me. For the texture bilinear adds, stacking the adds this way is similar to the exact same thing in terms of doing the ors. So if we want to, you can phrase them the opposite way. It's a little bit hard to read because there's so much stuff going on here. But there's the add PS of these 2 moles, right? And then you introduce the add PS of the other 2 moles, like so, right? There we go. And that's the exact same operation. Oops, I missed a parentheses there. So there's one add PS, there's the other add PS. There we go. What is my syntax error? What did I do wrong there? Did I miss a parentheses? I guess I must have accidentally cut something from this. Mismatched parentheses. Did I accidentally delete something from the add PS? Oh, I see what I did. I preemptively deleted the add PSs from there. All right, sorry. So R, PA. Let's see, here's the G's. Here's the B's, the A's. There we go. And so that's the same operation, but not dependent. Oops, I must have missed something there, though. So we're add PS, the 2 adds. There's the mul. Texel A, B, C, D, R, G, 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 B, B. Oops. There we go. There we go. But again, like, I don't know that that actually helps us much. I really don't know in practice if that, how important that actually is, right? Because I don't know, the compiler, we're already telling it that it doesn't have to obey our order of operations particularly hard. So I really don't know how much that really changes life for the compiler in practice. You really just have to time it to see if it actually made any difference. It certainly didn't make any difference in our particular case, right? If you take a look at what's happening, we're still at that many cycles. But we haven't gotten down to, maybe it would matter more if we had finished out everything. I'm not sure. Can you compile O2 to compare it to last week's parts? We are compiling O2. So we are, right now we're about 3 times faster. Why did you make macros for your SIMD operations versus making functions? Because, again, I just want to take any variability out of it. Macros are a straight text substitution. I know the compiler cannot mess it up. Whereas functions, the compiler might get confused, or, you never really know. Are these intrinsics the same on other operating systems or compilers as long as it's using the Intel architecture? Yes, these are the same as they would be in LLVM. The only thing that's not the same is the part that we're actually only using for testing, which is this M macro. So accessing, oh wait, no, never mind. I wrote it in the way that works on both architectures. Accessing these on Windows, on Visual Studio, MM128s are a union that allow you to access their components using the union. And on LLVM, they are not. But it looks like I wrote it in the way that works on both platforms to access a member, which is to cast it to a pointer. That works on both. So yes, so this code should work the same on any Intel compiler at the moment, GCC, LLVM, or Visual Studio. Why do you say unaligned store is nasty? As far as I know, for latest Intel CPUs, at least starting from Ivy Bridge, unaligned store and load is not very expensive anymore, less than 5% difference. Well, first of all, 5% difference is a lot of percent, right? When you're talking about optimization, you don't want to just go like, oh, let's ignore that. But the other thing is, it depends on the processor, right? Unaligned stores could be very expensive in the old days. And it also is very important to think about because some processors, such as like Xbox 360 and so on, don't have the ability to do unaligned stores at all, or they're extremely expensive if you do them, stuff like this. So typically, if you're talking about writing an optimized routine, most of the time, you want to come at a perspective of, I'm going to keep everything aligned, right? Because usually you can. It's not that hard to do so. And so typically you want to keep everything aligned that you can keep aligned. That just tends to be good policy. It also is better for cache alignment because if we're unaligned, if we're not aligned to a 16-byte boundary, it means we're also not cache aligned. And so that's another problem, which means you probably won't get as good a cache utilization. So in general, we probably want to take a look at that alignment stuff. Now, if it turns out that underfilling and overfilling are more expensive than the cache alignment or more expensive than the store alignment penalty, that stuff, then by all means, you use unaligned. So, if you end up in a situation where unaligned is faster, you use unaligned, right? But in cases where you can get aligned, and you probably want to check to make sure that aligned isn't going to give you a speed win because, Is scalar access to M128 elements still slow on Intel? Well, it's not slow, but it was never that slow, but it's always a downshift, right? Accessing the elements out of an M128 means A, you take a 4x speed hit right off the bat because you're operating on individual elements instead of all 4 elements at once. So you're 4 times slower before you even talk about anything else. Well, I shouldn't say you're 4 times slower. You lose the 4x speed increase. And then you're talking about however long a particular processor flavor from Intel takes to move stuff out of the wide registers into a regular register. So you've got issues. Brain Cruiser says the processor window is 192 instructions. So yeah, I don't know how long the processor window is on this particular processor, right? The processor windows are not always the same size, I believe. So saying it's 192 instructions, I think, is not necessarily accurate. And plus, are you sure it's 192 instructions, not 192 micro-ops? Because those are different as well. But regardless, the processor window is probably large enough that a lot of our routine is in it. And so that's why, say, ordering the instructions is kind of hard to think about because the processor will do, will do whatever it wants to do. Gasto5 says, I don't understand how one optimizes by using the intrinsic or function. I'm not sure what that means, but the idea behind the intrinsics is just that it gives you access to operating on things 4 wide. So right now, what we've done, the reason why we got 3 times faster already is just because we have switched to operating on 4 pixels at once instead of 1 pixel. That's all we did. And that's what the intrinsics allow us to do. convert PS EPI 32 always truncates. Would that be better than mess around with the rounding mode? Is that true? I actually didn't remember that. If that's actually true, then yes, that's much better. I didn't know that it always truncates. Let me see if we can. I could look it up in the Intel architecture manual, but I was hoping. to see conversion intrinsics. Convert PS. How is it possible that they wrote all this documentation? Okay, here we go. Oh, convert TPS. I see. Okay, I see what you're saying. Now I'm on the same page as you. Yes, convert TPS. I don't think that's SSE2. Is it? Is that actually SSE2? Let's find out. Wow, that's actually SSE2. I had no idea. Convert packed single precision flow meters with truncation and store the results in test. I did not know that. I had no idea that was true. That's awesome. And the answer, I think, is yes. That is exactly what we should do. And thank you very much for that suggestion. Because that was way better than what I was going to do. Honestly. So that's pretty great. Yes, I think that's an excellent idea. That just means we do have to do extra instructions here. So one might argue maybe we should try to set the rounding mode instead, but should we set the rounding mode to nearest and save the adds? We can say that, but what I'll do here is I'll just say, okay, you know, these are going to be add ps, and this will be like half. 4x, like so. I'm going to leave it like that for now because I think that is a good idea that you had. I don't know. I mean, it's going to cost us those 4 extra instructions is the only thing to do that extra add. And there's not really another place we can hide it, I don't think. So, you know, it's something to think about. But for now, I think that's a good, you know, that's a good compromise. So let's do half. Set 1 PS 0.5. All right. So there we go. That's pretty good. We're zipping around, right? You remember how slow this was when we started? It was like awful, right? And now we're totally rocking. All right, so that's all good. Good. Let's see here. So I think we're all set with that. Let's see if there's any other questions. All right, looks like we're all done. Let us wrap up. I believe we are done. So, we got a little bit more to do. Tomorrow we have to obey should fill. That'll be pretty easy. If you want to take a crack at it yourself, you are welcome to do so tonight to see how you do. It's not too hard, but it isn't something that we covered really how to think about necessarily. So yeah, but we'll talk about it tomorrow. If you want to give it a crack yourself, you can go for it. And then tomorrow, most of, I imagine, what we'll spend our time doing is this stuff. Right, so getting in here and starting to try and turn this into stuff that can operate 4 wide or as close to 4 wide as possible. That is really what the remainder of our job is. So we'll dig into that, and then we're getting pretty close. Right, there's not a whole lot else in this routine that needs to be converted, and so we're getting close to the point where we can kind of take a look at it and make an honest assessment and say how many cycles do we think this could run in. You know, best case. How close are we to that? And more importantly, how close are we to our goal of you know, making something that can run reasonably well at our resolution? Because we can go also kind of back out and say how many cycles per pixel, you know, if this routine ran at this many cycles per pixel, what would our frame rate be, assuming certain concepts about our sprites and that sort of stuff. So anyway, that's about it. We will do that tomorrow at 5 p.m. Pacific Standard Time. We're back to our normal time tomorrow. Let me go ahead and close this stuff off. And I will save our Blackboard. There we go. So, thank you everyone for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always, and a pleasure optimizing with you as always. And we will continue our optimization stuff tomorrow when we'll tackle those two things I was just talking about. If you would like to follow along at home and try your own hand at some optimization, you can always pre-order the game on handmadehero.org, and it comes with a source code, which you can download every night after I finish and sort of play around with. It's great for learning. You can do that on handmadehero.org. You can also check out our Patreon page if you want to support the video series. You can subscribe to that. You can check out our forum site where you can ask questions or check out ports to Mac and Linux, things like that. And there's also, of course, the tweet bot, which tweets the schedule at you. So if you want to catch the series live, that's the place to go. It always has an up-to-date schedule on there, so you can find out if a stream gets rescheduled or if there's a weird schedule for the week. That's the place to find out. Thanks for joining me. I will see you guys tomorrow. Until then, have fun programming.